Hello and welcome to NPTEL online certification course on aero engine gas turbine cycles. Today is lecture 10. In last lecture we were discussing about the introduction to combustion chamber. We were discussing about the construction detail for the combustion chamber and different types of combustion chambers. Then we tried to analyze as per our requirement based on control volume approach for the analysis. Then we were discussing about the combustion process on TS diagram, and we have introduced the performance parameter which are related with the combustion chamber like combustion efficiency and total pressure loss. If we look at, because we are having say very high heat generation per volume, that is what is differentiating this combustion chamber from other applications. Then we were discussing about different requirements from the combustion chamber and some of the fuel properties which we are using for our gas turbine engines. So, now let us move towards the next. So, here if we look at, this is representing single spool turbojet engine, and for that turbojet engine we have discussed about say diffuser, we have discussed about the compressor, combustion chamber. Let us focus today a very important device, that is what is called turbine. Now, here in this case, let us take the same engine what we were discussing for the construction detail. So, here if we look at, this is representing Pratt & Whitney 4000 high bypass ratio engine. So, in construction as we have discussed, we are having fan, LP compressor, HP compressor, then we were having combustion chamber. Now, the situation is very high temperature, very high pressure gas which is coming out from the combustion chamber, that is what will be entering inside the turbine. Now, the situation is the flow which is coming out from our combustion chamber that has low velocity, maybe mark in the range of 0.2, 0.3, and we want to accelerate our flow because we want to utilize the force that is what is coming out from this high temperature gases, and that is the reason why this is made up of. So, if we look at here, this device, particular device, that is what we are defining as a HP turbine. So, in this case the flow which is coming out from the combustion chamber, that will be entering inside this device, that is what is called nozzle. So, do not get confused, here this is what is called nozzle. So, the purpose here it is similar. If we look at carefully and if we will go along, we will discuss what is a construction detail for this nozzle. So, nozzle if we look at, my entry area that is what is higher and my exit area that is what is smaller. So, that is what is representing the conversing passage. So, this high temperature gas, high pressure gas which is coming out from the combustor, that will be passing through these stationary nozzles. Then that gas that will be striking on the rotor blades, which will bring the rotation of this wheel, and we can say we are extracting the work from our working fluid, that is what is gas, and that will lead to give the rotation to this wheel. This wheel which is connected with our compressor, means if I will be having the rotation of my HP turbine, that will give the rotation to my HP compressor. So, we can understand now this turbine, that is what is a power generating device. If we move downside and we observe carefully, here this also is representing the turbine, and that turbine it is defined as a low pressure turbine. Now, what we mean by low pressure turbine and what we mean by HP turbine, that is what is same. Here my operating pressure is higher, and that is the reason why it is called HP turbine. In the case later side, because of my expansion process, we say my pressure that is what is decreasing downside. That means on the downside we will be having our pressure that is what is decreasing, and that will lead to operate this turbine at the low pressure, and that is the reason why it is called LP turbine. Okay. Now, LP turbine if we look at carefully, it says my entry passage and exit passage area, they are different. Now, the question is what is the reason? So, if you recall, when we were discussing about say compressor, that time we were discussing my mass flow rate that can be represented as density into area into velocity. Here in this case we know my pressure and density, they are in direct relation. For compressor, with rise of pressure our density was increasing, and if we are assuming our velocity to be constant, we can say my area, that is what is decreasing area, because I want to maintain my mass flow rate constant. Similar to that, here in this case when I am moving downside, my pressure is decreasing, that means my density also is decreasing, and if I consider my velocity to be constant, we can say my area need to be higher. So, there is no other reason for having these blades to be of say more height. So, these blades they are say short height blade, these are say tall height blade. So, here if you look at, these are the blades for my LP turbine, and here if you look at carefully, this is representing the HP turbine blade. Now, very interesting to observe here, the temperature at which my gas is coming out, that will be in the range of maybe 800 Kelvin to say 2000 Kelvin, depends on engine manufacturing company. So, because it is subjected to very high temperature, and this metal what we are using, that is what is say nickel alloys. So, that metal has some melting point temperature. So, that cannot sustain very high temperature. In order to maintain the temperature within the limit, just realize one thing, what we say, we want to maintain the temperature limit, that we say as a cooling. So, in order to have this blade to be cool, there are special kind of arrangements they are being made on the surface of the blade, both on pressure surface as well as suction surface. This is the provision for HP turbine nozzle as well as HP turbine rotor. If you look at on the top side also, we are having the cooling holes from where my cooling air, that is what will be coming out. In some cases, special engines HP turbine initial stages are also required the cooling. So, you can understand this is what is representing the thermal cooling. Okay. So, we are not completely cooling the blade. Remember one thing, what we are doing basically is we are maintaining the temperature of this blade in a safe range. In order to have this cooling, we need air. So, basically air is used as a working fluid. So, here in this case, if we look at, since my operating pressure, that is what is higher, that means my injection of air for cooling purpose, that also need to be supplied at high pressure. So, tapping, it is been taken from HP compressor, and from there it is been supplied to my HP turbine. Otherwise, if we will be taking say low pressure entry, then my flow will be going reverse, means from high pressure side to low pressure side. So, that is how the cooling arrangement it is been made with. Okay. Now, let us move to the next. Here if we look at, this is representing our PT6 engine, that is what is been used for propeller engines, and if we look at carefully, here we are having compressor, that is what will be followed by my combustor. This is what is my turbine. The turbine, if we are looking at, we are having say 3 stage of turbine. Out of that, one turbine stage, that is what has been defined as a power turbine. So, realize one thing, what turbines we are using for the rotation of my compressor, that is what is sufficient to generate the power for the rotation of the compressor. Now, more amount of work we are extracting by using this power turbine, and by this power turbine we are connecting that with the gearbox and the propeller, and that is what is used to rotate the propeller wheel. Now, here one more important thing is, like what gas, that is what is coming out from the turbine, that is what basically will be used for say generation of thrust in nozzle. We will discuss the next component is nozzle, there also we will be discussing this part. So, some amount of work that is being extracted from this gas coming out from the previous stages of turbine, and that is what is being utilized for rotation of our propeller. Now here the purpose is not the generation of thrust by means of nozzle. Okay. Here this is what is representing very famous engine, that's Honeywell engine. This engine, it is having say 18 models and different 106 configurations, and if you look at carefully here in this case we are having two centrifugal compressor, that's what will be followed by the reversible combustor, and here we are having turbine stages, and this turbine, that's what is being used to rotate our compressor as well as for the rotation of our shaft. This shaft can be used for both the purpose, maybe for the rotation of say propeller or maybe for the rotation of say rotors for the helicopter engine. Here this is what is representing the helicopter engine. We can say this power turbine, that's what is been connected with this shaft by gearbox, and that's what is been used to rotate our rotors for say helicopter wheel. So this is what is very interesting case. Same way if we look at carefully this aero engine, that's what is we have discussed mainly for aeroplanes, for aircrafts. The whole purpose for the turbine, it is to rotate only compressor. In the case of my turboprop engine and turboshaft engine, we are having power turbines. Now similar kind of construction we will see for land based power plant, because for the land based power plant there also we will be having additional turbine stage that will be connected with our generator and which will be used for generating the electricity. Okay. Now in overall if we look at what it says, now in terms of thermodynamics we can say we are having high pressure and high temperature gas, that's what is coming out from the combustion chamber. That's what will be having very high potential energy. Now this potential energy which we are converting into kinetic energy, this kinetic energy that will be rotating our wheel, and that rotation we are utilizing, we are extracting the energy from this wheel by virtue of our aerodynamics and aerothermodynamics, which will be converted later into mechanical power, and this mechanical power as we have discussed, that is used to rotate the compressor for aero engine. This is used to rotate both compressor and generator for the land based power plant, and as we have discussed for turboprop and turboshaft engine we will be having additional turbine stage, that's what is used to rotate our shaft for propeller as well as for the rotors. Okay. Now let us try to understand this expansion process which is happening inside the turbine. Here if we look at, this is representing the stator or my nozzle vane, and I am having rotor wheel. As we have discussed, my flow, that's what is flowing from this direction. Let me put different stations. Station 1 at the entry of my nozzle vane, station 2 it is at the exit of my stator vane, and station 3 it is representing my rotor exit. So we know we are having high temperature and high pressure gas which is coming from combustion chamber. It is entering with some pressure say P01. If I will be putting say my velocity component, then that's what will be giving me my static pressure at the entry of my turbine. Now here from 01 to 02, that's what is representing my process which is happening inside the stator or in the nozzle vane, because we are having no extraction of work, that's what is happening. We are considering that as adiabatic process, and that's the reason why my T01 and T02 they both are same. But since it's a solid device, we have discussed it will be subjected to the loss, and this loss we are representing in terms of total pressure loss. Now based on my velocity component we can locate my point 2, that's what is representing my static pressure. If I will be connecting my points say 1 and 2 dash, that's what is representing the isentropic expansion happening inside my say nozzle vane. And if I will be connecting these two from 1 to 2, that's what is representing my actual work process. Okay. So you can understand this delta S what we are observing, that is nothing but it is representing the irreversibility associated with the process. Now from this nozzle if we consider, we will be putting our relative velocity component, and that's what will lead to give me P02 relative, and this point I am putting as a T02 relative. So, for stationary component we are considering absolute velocity component, and for rotating component we are considering relative velocity component. Sometimes people they are defining as say rotating enthalpy, or it is also called rothalpy, and here for the nozzle vane we are writing that as a enthalpy. So, here it is representing rothalpy. So, similar logic, that is what we will be putting in terms of rotating reference frame, that is what will be giving me my P03 relative. Here my T02 relative and T03 relative, they both will be same. So, I can locate my point 3, that is say P3 point, and this location is 3 point. Now, from 2 to 3, that is what is representing my actual work, that is what is happening inside the rotor, and this is what is representing my isentropic work, that is what is happening inside my rotor. So, you can say this overall, that is what is representing our rotor work as well as my nozzle vane work. Now, in terms of representing the overall process, we can say that is what is from 01 to 02 to 03. Now, if we consider my thermodynamic work, then this is what is representing the work done or work, that is what will be generated by the turbine, and that is what is given by W equal to m dot Cp T03 minus T0, say T01 minus T03. Okay. Now, let us move towards the next. As we have discussed, over the year we are moving more towards the generation of more and more thrust, and we are looking for our weight of our aircraft to be lower. So, we can say we are moving towards thrust to weight ratio to be as high as possible, and in order to achieve that we need to have our engine to be efficient. When we say engine to be efficient, then it need to fulfill certain requirements in terms of pressure as well as temperature. So, it says we are moving more towards say higher and higher temperature side, because this what we are discussing about the gas turbine cycle, it says with higher turbine entry temperature we are able to achieve higher thermal efficiency. When we will be discussing the cycle in detail, that time we will be touching this point, but at this moment you can understand over the year the turbine entry temperature, that is what has been rising. So, here if you look at initially up to say 80s we were having uncooled blades, then after the film cooling, that is what is been incorporated, then after we are having thermal barrier coating, without thermal barrier coating, and then later on people they are exploring at this moment for say using heat pipe cooling. And there are different kinds of material what we were discussing, they are inconels, directionally solidified kind of inconel material, single cluster blade. So, this all are representing the new materials which are being developed for say gas turbine blades. Okay. Now, same way what we have discussed for our compressor, we can use this for our power also. Say power, that is what will be extracted here for the turbine. So, we will be using our concept of say angular momentum. Here in this case you can say this is what is representing say turbine blade, and this is what is representing my rotational speed. Say my entry radius we can consider R1, and my tangential velocity I say CW1. At the exit we will be having my radius as say R2, and my tangential velocity, that is what is CW2. So, what we have discussed for the compressor, in line to that only we can say we can apply our angular momentum conservation equation, and that is what is representing the term, it is called torque, and this torque it is written by m dot into CW1 R1 minus CW2 R2. Once we know what is my torque, and if we know the angular velocity or the rotational speed, we can calculate what will be the power. And it says if my tangential velocity, that is what is decrease across the blade, that means positive tangential velocity, that is in the same direction of rotor motion, then we can say we are extracting the work from the working fluid, and that is what is defined as a turbine. Okay. Now, this is what is very important when we will be discussing the configurations for different engines. We will be touching this point again. Now, let us try to understand, as we have discussed for the compressor, we are having our blades, they are having aerodynamic shape and they are having say aerofoil shape. So, here if you look at, this is what is representing the aerofoil, and for this aerofoil I can say it is defined as uncambered aerofoil or symmetrical aerofoil, and this aerofoil if I will be putting in the flow without any angle of attack, we can say this aerofoil will not be generating any lift. Be careful. Okay. Now, I will be giving some curvature to this blade. So, here if you look at my flow, that is what is entering at some angle here, it will be passing through the suction surface and my pressure surface, and later on it will be moving downside towards the trailing edge. This is what we say as low cambered aerofoil. Okay. When we are having this camber, we are putting this camber, that is what is giving me the differential pressure on pressure side as well as on the suction side. That is what will lead to give the lift force, and that is what is very important, and perpendicular to that, that is what we have defined as a drag force. Now, let me give the large camber like highly cambered aerofoil. For that also we will be getting lift force and we will be getting the drag force. Now, here it is very important to understand, we have our basic understanding about the aerodynamics. If we consider, say, this is my configuration, suppose say 2 aerofoils or 2 blades are arranged in this way, where my entry area is lower and my exit area is larger. We can say, if we recall what we have discussed, this passage is representing the diffusing passage, and here my entry pressure and exit pressure, that is what will be different. How it will be different? My entry pressure will be lower, my exit pressure will be higher, because I am diffusing my flow. Similarly, if I will be arranging my aerofoil in this way, where my entry area and exit area are different. So, here my entry area is higher, my exit area is lower. That means, this passage is representing converging passage. So, I am having diverging passage and converging passage. So, if we look at here, let me put the lift force for both the cases. So, here in this case, in order to raise the pressure, we are utilizing the lifting force. So, we will be giving the rotation of our wheel from suction side to the pressure side, and this process here, if we want to extract the work from our working fluid, my gas will be passing through that, we will be using this lifting force in order to extract the work, and that is the reason why the direction of rotation will be from pressure side to the suction side. So, here this is representing the compression process and this is representing my expansion process. So, remember one thing, my entry pressure is lower for the compressor, exit pressure that will be higher for the compressor. For expansion process, my entry pressure will be higher and my exit pressure will be lower, or you can say here we are reducing our flow. Okay. Now, suppose if I will be arranging this and if I will be representing my force, those forces I can say it is a lift force and drag force. Let me put other force components here. So, I say I will be having one force, that is what is acting in the direction of my flow, and second force, that is what will be acting perpendicular to this flow. So, this I am representing as say Ft and this force I am representing as Fa. So, here we need to realize what Ft is representing say my tangential force, and Fa, that is what is representing my axial force. Now, if you recall what we have discussed, say this tangential force, that is what is basically responsible for my work extraction or work consumption. So, here we say my torque required to be supplied, we need to supply the torque in order to do the compression for compressor, and we are extracting our torque for the turbine, we want to extract the work from that. So, this tangential force, that is what is responsible for our work extraction or work consumption. Second force, that is what is very important. So, if you recall, in first week we were discussing all our engine components, they are generating the thrust. Okay. So, this axial force, that is what is basically generating the thrust. So, if you recall, we were discussing for our compressor, that compressor stages, they are also generating the thrust, and that thrust we say it is in forward direction. So, this is what is the meaning of that. I told, like when we will be discussing about the construction for compressor and turbine, we will be discussing this point. Same way for the turbine, I will be having my thrust or my axial force, that is what will be in the rearward direction. So, just realize, just understand this part, how we are utilizing our turbine. Now, let us apply say control volume approach here. In this case, this is what is representing my turbine. My entry condition is 5, entry condition is 4, exit condition is 5. Here in this case, mass flow rate, that is nothing but fuel air mixture that will be entering inside the turbine, and this is representing my exit condition. Suppose if I consider there is no bleed or no leakage, we can say my entry mass flow rate and exit mass flow rate, they are same. We can say adiabatic process where my Q is 0. My W here, that is what is greater because my shaft work, that is what is crossing the boundary. Here in this case, we are getting the work from the turbine, and that is the reason why this is representing the positive work. So, if I will be writing my equation, energy equation, it says my Q equal to 0, my W is greater than 0. It says my W, that is what will be coming as minus delta H, and therefore, the working fluid, the enthalpy decrease in the turbine. So, we can say my fluid gives energy to the turbine and the shaft. Okay. So, we need to realize, we need to understand this energy equation thoroughly. Same we have seen for the compressor where we are having say W, that is what is positive sign. Okay. Now, in actual process, as we have discussed earlier for the compressor, here also we will be having valve friction, that is what will be present because of growth of boundary layer. That is nothing but it is my viscous effect. I am accelerating my flow, that may be possible that my flow will be going supersonic. When we will be having that kind of flow, we will be having shock waves which are forming, and that will lead to increase the losses, and it is increasing the irreversibility with the process. Okay. And if these together, if we will be combining, it says it is increasing the losses, and that is what we are representing in terms of entropy. Here we need to be very careful, say the loss mechanism what we are discussing at this moment for the turbine, it says because of presence of these losses, my entropy always has tendency to increase, and that is the reason why in actual we will be getting our exit temperature to be higher than that of my isentropic expansion process. So, let us look at that. Here if we look at, this is what is representing my entry pressure and my entry temperature, and this process from 404 to 05, that is what is representing my isentropic work, and this process from 04 to 05, that is what is representing my actual process, and here if you look at, this is representing my entropy, okay, change of entropy delta S, and as we have discussed in actual process my T05, that is what will be greater than that of my T05S. Okay. Now, once we have understanding about that, then we will be putting the new term, that is what is called my adiabatic efficiency. For the turbine, that is what will be given by my actual work divided by ideal work. If you recall, for the compressor, as I told, it is a power consuming device, and that is the reason why we were having this equation to be in a reverse way. Here this is what is representing my power generating device. So, do not get confused in terms of definition for the efficiency. So, here this is what has been given by H04 minus H05 divided by H04 minus H05S. This represents my isentropic work. So, I can write down my temperature ratio in terms of pressure ratio or expansion ratio. Here let me introduce two more terminologies. That is what is my expansion ratio. It is given by P05 by P04 and my temperature ratio is T05 by T04. And if I will be analyzing this term, it says my efficiency, it is a function of my temperature ratio and expansion ratio. Okay. Now, this is what is representing my overall work done or overall process of the expansion. We have discussed like my turbine, it is comprising of number of stages, and if I say per stage, then that we are defining as a polytropic efficiency. So, we have discussed similar to turbine in our compressor also, per stage efficiency we are defining as a polytropic efficiency. So, here this expansion process, if we look at carefully, this is what is my first stage expansion, then this will be happening in second stage, this is what is representing my third stage. It is very interesting to observe what we have discussed for my compressor and for my turbine, they both are different. Here in this case, my isentropic temperature delta T0, that is what will be greater in the case of my overall stage configuration. When I will be going with the multi-stage configuration, my delta T0, that is what will be say lower. Okay. Now, where will it be reflecting? That is what we will be defining in terms of our polytropic efficiency. So, polytropic efficiency we are writing in terms of dH0 by dH0s, and by using our second law of thermodynamics, we will be coming out with the term. It says my polytropic efficiency, it is given by Cp dt0 by RT0 and dP0 by P0. Based on our fundamental equation, if we will be going for integration and simplification, it says my turbine efficiency, that is what will be given in terms of polytropic efficiency like this. Okay. So, this is what is representing my equation in terms of polytropic term. Okay. So, here if you look at, this is what is representing my adiabatic efficiency when I am considering say maybe one stage or the overall stages. Here it is representing when I will be having my turbine, it is comprising of number of stages. Now, this is very important. So, let us try to analyze this part, how it will be used. So, let us take like it says the improvement in the polytropic efficiency from say 0.9 to 0.92 for the two expansion processes like say 2.5 and 4, we need to calculate what will be the isentropic efficiency. So, here in this case what information is given to us, it is say polytropic efficiency of the turbine, that is what is given, and expansion ratio is given. We want to calculate what will be my isentropic or what will be my adiabatic efficiency. So, let us look at this part. So, here if you look at the turbine isentropic efficiency, that is what will be given in terms of my temperature ratio, or we can say here. So, here what information, that is what is given to us is in terms of say my ratio of expansion to be 2.5 and polytropic efficiency to be 90%. If I will be putting that in this equation, it says my efficiency is coming 0.939. So, it is approximately 0.94. So, you can say for this expansion ratio, we are having this efficiency to be 0.94. Now, for the same expansion ratio, let us take the polytropic efficiency to be 92%, and let us see what is the change we will be getting. If we say if we are taking this expansion ratio to be same and polytropic efficiency to be higher, that is what will be giving me my adiabatic efficiency to be 95%. So, here if we look at, this is what is representing the higher value. Now, let us take the expansion ratio to be 4 and same polytropic efficiency. So, if I will be putting my expansion ratio to be 4, it says my efficiency is coming 95.46%. Same way, if I will be taking my efficiency to be 92%, it says my efficiency is coming 96.35%. Now, this is what is very important. If you recall, the similar kind of discussion we have done for compressor. So, let me join these lines. That is what is representing, say, two polytropic efficiency variation with different expansion ratio. Now, here in this case, it is giving some more information. What it says, if I will be having higher polytropic efficiency, I will be able to achieve higher adiabatic efficiency. Okay. Now, what is the meaning of that? It says, it will be asking the logic to us, like, do we add more number of stages? Because what is the meaning of polytropic efficiency to be higher? It means I am dividing my work into more number of stages. If it say yes, then it says, wouldn't it be adding the losses? Yes. So, here in this case, what we know, my turbine basically it is working under favorable pressure gradient. Favorable pressure gradient in the sense my entry pressure is higher, my exit pressure is lower. In that condition, the chances for my flow to get separate, that will be less, and that is the reason why I can take per stage expansion to be higher, and that is what will be lead to reduce the number of stages. So, opposite what we have discussed, if we are talking about the compressor, we have seen the compressor, it is working under adverse pressure gradient. I cannot go aggressively in terms of increasing the per stage pressure rise, and that is the reason it says we need to go with more number of stages. Okay. Now, it says my energy exchange, that is what is happening inside my turbine rotor. So, it says more the number of stages, that will give more opportunity for energy to be converted into shaft power. So, opposite sense what we have is a power consuming device. If we will be adding the more number of stages, that is what we increasing the losses in the process. So, if you recall the plot what we have seen for my compressor, it says with the increase of my pressure ratio, we will be having say decrease in adiabatic efficiency, and that is the reason it is rightly said the turbine stages may be thought as opportunity, more number of compressor stages that can be considered as a burden, but you have no choice here for the compressor. The reason is, as we have discussed, because it is an aerodynamic entity where it is working under adverse pressure gradient, you have more chances for the flow to get separated. The separation of the flow that will lead to reduce the operating range and performance, even efficiency. Okay, and that is the reason why you are not having choice to reduce the number of stages for the compressor. But for turbine, if we look at carefully, we are having the opportunity because it is working under favorable pressure gradient. That is what will be giving like per stage expansion we can get higher, and that is the reason you just try to search on internet, maybe just look at what all we are discussing at this moment. If you look at the cut section of your engine, mainly aero engines, you will see you are having more number of compressor stages and my turbine stages are less. Suppose if I say military engine, you will be having maybe 8 or 10 or 12 stages of compressor, but that is what will be run by maybe one stage of HP turbine or maybe 2 stage of HP turbine, that will be followed by 1 or 2 stages of LP turbine. So, there the consideration is what we are looking for in terms of reduction of weight and reduction of size of the engine, because both of them they are the major requirement for the military engine. Suppose if you recall what engine I am displaying again and again, that is what is for Pratt and Whitney engine, where we are having more number of stages for HP compressor, more number of stages for LP compressor. Same way it is having only 2 stages for HP turbine and multiple stages for LP turbine. Now, the situation here is we want to rotate our front fan at the lower speed. It has so many aerodynamic, aeroelastic, mechanical issue with the fan, and that is what is demanding my fan to rotate at the lower speed. and in order to rotate that wheel at the lower speed, we are extracting less amount of work by incorporating more number of stages. So, just try to recall this part, because that is what is very important to understand. So, this is what is the end of today's discussion. So, let us see what all we have discussed. We started discussing about our axial flow turbine, what we are using for our aero engine, and we have seen we are having different spool configuration, HP spool and LP spool. We have seen how the expansion it is happening on HS diagram. Then we have taken our approach for control volume in order to analyze the flow. Then we have introduced the efficiencies called polytropic efficiency, isentropic efficiency, and we were having good healthy discussion in terms of what is the criteria for the selection of number of stages for the turbine. So, here we are stopping with. In next lecture we will be discussing the next component. Thank you very much.